Hello there. My name is Andrew Bridges and I'm the President and CEO of Photron USA, a wholly owned subsidiary of Photron Limited of Japan, the world's largest manufacturer of high-speed video cameras for slow-motion analysis of events that occur too fast for the unaided eye to see or understand. But today I wish to talk about our high-speed 2D polarization camera, the Crysta, and how it can be utilized to image stress distribution in transparent materials. We all appreciate the glass reducing benefits of polarized sunglasses, and you've probably all noticed while wearing your polarized sunglasses the normally invisible crazy patterns in automotive and architectural tempered glass. This is stress, intentionally induced to ensure should the glass break, it will do so in a controlled manner and not shower the vehicle's occupants with razor-sharp shards of glass. But polarization can also be utilized to show us phenomena sometimes referred to as photoelasticity. Why polarization? Well, there are many ways of imaging what is occurring on the outside of an object. Digital image correlation, infrared imaging, and conventional high-speed cameras to name just a few. But what happens if you want to see what is taking place within the object beneath the surface? You can clearly see in the lower pair of videos how utilizing ultrasonic vibration greatly reduces the stress induced in the material during the cutting process. How else could you so clearly demonstrate this improvement? What is birefringence? Well, crystalline materials can be classified as either isotropic, where refraction is symmetrical, so the same regardless of the direction of the light passing through the material, for example glass or even sodium chloride. However, some materials are anisotropic, meaning they have a physical property that has a different value when measured in a different axes. Wood is a great example of an anisotropic material. It has two distinctly different axes and is much stronger along the grain than across it. Calcite is another example where light is refracted into two rays, often referred to as either the slow and the fast or the ordinary and extraordinary rays. And these rays are dependent on the refractive index of the material. One of these rays will typically travel slower than the other, and this difference is defined as the retardation and is typically measured in nanometers. Birefringence, or double refraction, is the optical property of a material having a refractive index that depends on the polarization and propagation direction of light. Well, the Crysta, as I've mentioned, is a high-speed 2D polarization camera, and to make this we took your common or garden 1 megapixel high-speed CMOS sensor comprising of 1024 pixels wide by 1024 pixels high, each pixel being 20 microns square. Then we added the necessary circuitry to enable it to operate at full resolution of 7,000 frames per second and reduce resolution up to 1.3 million frames per second. Next, we sputtered a pixelated polarizer array made from photonic crystal directly onto the sensor on a pixel by pixel basis. The photonic crystal lattice features pixels in groups of 4 square, each having a different polarization axes at 0 degrees, 45, 90, and 135 degrees. And by applying phase shifting algorithms with circularly polarized incident light, birefringent phase difference and azimuthal angle can be measured to enable us to quantify and measure physical stress in transparent and semi-transparent solids and fluids in high-speed resolution. The benefits of high-speed 2D polarization. Well, traditional polarization systems typically utilize rotating or moving polarization filters. This prevents them from capturing full-speed two-dimensional data at any usable speeds. But by bonding the photonic crystal polarizer array directly to a high-speed sensor, with our pixels offset by 45 degrees from their immediate neighbors in clusters of 4, we can simultaneously expose all pixels and record high-speed 2D polarization data at framing rates of hundreds, thousands, or even millions of frames per second, and with very short shutter times if required. The benefits it gives you, the main advantage of course is the ability to see in high speed the entire picture or frame, not just one line or one specialized viewpoint at a time. You can see your entire area of interest recorded faster than in the blink of an eye. In addition to capturing the 2D area scan high-speed birefringence data showing what is happening inside the block of acrylic being drilled, we also retain the traditional monochrome high-speed view, high-speed monochrome grayscale data for later analysis and display alongside the polarization image. As mentioned, birefringence is the optical property of a material having a refractive index that depends on the polarization and propagation direction of light. These optically anisotropic materials are said to be birefringent. The birefringence is often quantified as the maximum difference between the refractive indices exhibited by the material. Retardation values that can be determined by phase difference of the X and Y components show the internal stress within the sample being tested and are relative to the material thickness and photoelastic constant of any materials being viewed. Our typical polarization imaging test setup comprises of a light source for the Crysta, in this case 520 to 530 nanometers, fitted with a left-hand circular polarizer. The sample for being testing transmitting a minimum of 30% light through it. In front of the optics we utilize a bandpass filter appropriate to the wavelength of the light source. And then conventional optics. The Crysta comes with both Nikon F/G bayonet mounts as well as the threaded C mount for mounting to a microscope or similar optics. And lastly, the Crysta with a high-speed CMOS sensor equipped with a photonic crystal polarizer. For our simple test, we took a 190mm tall by 95mm by 10mm thick piece of acrylic with a couple of holes and several cuts in it just to show residual stress patterns as well as induce some interesting astigmatism. This was then struck with a hammer at the top right-hand side of the image. Here's a video of the test I performed in my office. The 530 nanometer light source with circular polarizer is on the left, and the camera bandpass filter on the very front, and a 105mm Nikon f-mount lens affixed to the Crysta. As well as being able to display the retardation in nanometers and the fast axis orientation in degrees, we can also display the retardation across any line within the image area, time-space, which is the retardation as it changes through time on the line, and the values of any point in the displayed image. And of course, all data can be exported as comma-separated value spreadsheet data. We can also synchronize with other imaging systems, such as infrared. We have even seen experiments where the conventional high-speed Crysta data is used for digital image correlation to complement the retardation view, providing details of what is occurring externally and internally within the subject from a single camera. Here again, the polarization shows internal stress, this time in a film stretch test recorded at 120 frames per second. Note how the retardation image best shows the stress around the two nicks that is not visible in the IR view and enables us to analyze how stress is distributed around and contributes to the fractures. And here is a small selection of the different applications we have seen the Crysta employed for. Rheology, the study of non-Newtonian fluids, crystal structures, typically in the growth of semiconductor crystals, crack propagation, and materials testing, especially interest in the development of lightweight materials, and then processing and cutting of glass used in cell phones or tablets. Great deal of interest in the cutting process to minimize the micro cracks that develop in this cutting process. And the Crysta can be utilized as a key component in a piezo interferometer, in which the interference of two beams of light is employed to make precise measurements in optical density. Utilizing the Crysta as a key component of the interferometer, it is possible to visualize sound. This video shows the sound generated from castanets being clacked together, recorded at 100,000 frames per second. And the graph at the top is from a microphone. You can clearly see how limited and very two-dimensional that data is when compared to the color interferometer view. In this video, we can see at the top a common air duster, and the lower view shows the interferometer view of the compressed air blast and shows changes in optical density of the air around the blast. Interferometers are widely used for the measurement of small displacements, refractive index changes, and surface irregularities. And we expanded the polarized sensor concept to cover large-scale scanning of production lines. These can be up to 11 meters wide and several kilometers in length, utilizing multiple line scan cameras. enable engineers to see the different production process and the effect on the finished product. Thank you for your interest. Please feel free to contact me or my colleagues if you have any questions or would like to find out more about our polarization systems. Thank you for your time.